algorithms, you know phase transformation happen, and that change your crystal into different phases. That's why both thermodynamics and kinetic are important. And this is the slides from my kinetic professor in America. So he is really kind to share the slides and a general view of the overall phenomena in solid state, like including like crystal, semiconductor, ceramic. All the structural evolution is based on kinetics. Okay, you need to analyze it. So you can look at it. Look at my mouse. You see the grain size growing. That's very important. You know that. And also, precipitates mean how solid phase precipitate out of the solution, like a liquid phase. And that's also controlled by kinetic. And that's about the nanoparticle synthesis, right? Some of you use hydrothermal to synthesize nanoparticle, right? So you need to control the grain size. Kinetic will teach you how to calculate it. However, I only succeed on lecturing this kind of nanoparticle synthesis in the first year. For the following year, like in English version and pandemic issues, slow down the lecturing. So I never catch up to teach you guys how about the nanoparticle synthesis, nanowire synthesis in the solution phase. Well, that's the issue of English lecturing because I need to make sure you learn it well, you understand what I am saying. So it's slow, and that's why I sincerely suggest you take the Chinese version class to make sure you learn it well. Professor Su is a very good theorist, and his derivation, his mathematical logic, his physical logic are all good. So he's a really good theorist. If you learn his class well, I can guarantee your fundamental skill about kinetics, right? It needs to be derived by a lot of math, and he's a really good theorist. And, and okay, let's look at the slides again. And you can see a lot of different interaction between the structure and the material, like the grain boundary width, its location, and how your atom diffuse, how large your unit cell, and then how to grow microdomain in the polymer system. It's all about kinetic. And then you can look at the larger size, like wow, wafer size is also controlled by kinetic. Yeah, you need to grow a large wafer, right? I don't know what kind of job you will do. So it's also controlled by kinetic because it's about structural evolution from liquid to from molten silicon sand, right? Silicon solid molten one, and you grow it into uh, very good single crystal and silicon. Of course, that's controlled by kinetic. Structure growing is all about kinetic. It just happens in different dimensions. All right. So some other industry operation like welding, your wire bonding, and superconductor wire, the width is all about the dimension of space. And you need to analyze how structure change in particular dimension. It's a part of genetics. Okay, so and my professor rearranged the previous page and then put them into this new diagram in the concept of evolution rate. Okay, you can look at the speed of this kind of dimension, the structure evolution, by 1 millimeter per second or 1 micrometer per second, 1 nanometer per second. You can look at the evolution rate or the changing rate for different phenomena on the previous page. So he rearranged it and then put it on this new diagram. So you know kinetic is all about the rate of changing a system. That's kinetic. Okay, and you may ask, well, what's different about the thermodynamics? Yeah, thermodynamics define the equilibrium state. Kinetic define how those states changing themselves. Okay, so changing means certain rate, right? RATE rate. Okay, so kinetic is all about time and dimension, right? So you need to calculate a lot of math. That's not easy. And you need to take care of different phenomena in different length scale, as my professor rearranged this diagram. So we cannot cover everything, but I try to cover the most important thing. And you may ask, what kind of mechanism drives kinetic phenomena happen? And you can look at this page. It's all about defect. Okay, defect. Oh, by the way, I am not recording video. I don't care you attend or not. You don't count as your business. Okay, it's a synchronized class. I don't take the video. I don't record video. So I won't re-edit it. I won't repost it online. You don't count your business. It's not my business. Okay. And the defect-driven diffusion is the most important thing in the kinetics. All right. You will learn a lot of defect and how those defects drive structure changes in the crystal. So, and you may look at it since it's the changing system most likely in a crystal, and you need to have a sense like you should expect crystal structure determine something. Okay, I don't know what that thing is, but I'm definitely determining something. And that's logic, right? It's about crystal. Crystal has a particular structure. So you need to expect, okay, look at this page. You need to expect this kind of structure growing should have particular geometry. For this example, this is gamma phase nickel and grown with gamma prime nickel aluminum alloy grown on the top. So that's crystal structure different. And you can see some rectangular grown on the surface. So that means is 100% guaranteed, depending on crystal structure. Or how could you have a rectangular shape, right? You have no matter BCC or or simple cubic or FCC, it's all cubic. And that's why you need to pay attention to the crystal structure. Most likely I will teach you BCC and FCC. So they are different, but the idea is the same, okay? And some of you will be working on the semiconductor field. This is an example for gallium nitride. And you are growing crystal of semiconductor like gallium nitride. And gallium nitride is a very famous material that has very high crystal strength. Because gallium and nitride has very different polarity. Nitrogen is really, really negative, right? So that is a highly polar potential, the crystal potential, will drive the crystal growing crazy. Okay, the interaction is so strong because that's driven by almost Coulomb interaction, almost very strong. Coulomb interaction is the most important and the most phenomenal driving force in this kind of structural growing, and most likely the strongest one in the natural world. All right, it's so strong, so you cannot control it well. That's why you look at the picture, the right side, the D and the B. You can see a lot of dot lines, right? Those lines are dislocation. And look at the dislocation on the D and the D part. So massive. And you cannot control the crystal growing well. That's the typical problem for gallium nitride. And however, you look at the C part. C part looks clean, right? And what's the difference between the growth mechanism of C and D? Okay, can you see that? And you can also look at the top of left pictures. That's how people use mask to block any nitride crystal going directly. Because they learn this in a painful way. They know any nitride cannot be well controlled. So the part that's unmasked by SiO2, silicon dioxide. So you can look at that part. The part B, look at my mouse. This B part is the open part here. Okay, it's open part here. So if you grow crystal directly on top of the open gallium nitride space, and that's this deep, you cannot control it. So massive, so many dislocations. So the material efficiency is really low. Gallium nitride is a blue LED material, and it's really important material. So blue LED won Nobel Prize. That's why you know it's so important. That's a huge breakthrough in the human industry. And why on the black area you can grow gallium nitride so well? Have you sensed the difference? Anyone want to answer? And remember, I have mentioned to you, it's all about crystal. Anyone want to answer it? Why the C part can be grown well? Yeah? No one? No one want to answer? Or no one in the class? Yeah, try to answer it. In the time I'm drinking water. Anyone? I don't care you want to type it or you want to speak it out. Why crystal growing are so different on these two different areas? I have mentioned some thinking clues. You need to connect it together. I have told you gallium nitride is a very polar material. And you can see the defects are grown on the vertical direction. And I also said you cannot control the highly polar, the Coulomb forces really well. So all those thinking clues connected in a logical way and lead you to the answer. Maybe that's the problem. Online lecturing is really slow. No one try to answer me. No one pay attention. Okay. No one try to answer me. I told you it's Coulomb force. You cannot control it. Since you cannot control, it's really defective. And however, you look at the C part, it's clearly different compared to the D part. So what does that mean? Combine these two thinking clues. What's the logic answer? Now you guys have seen the problem, right? So I told you you need to answer my question or you are not thinking. If you are not thinking, you are not 70% people most likely will fail. Okay? Attending this class, that you only wasting your time because you are not thinking. You cannot learn the logical thinking. If you are not a logical thinker, you most likely will have trouble in your future career. And you are only a technician. You cannot think to do develop. That's the problem. And you are waiting for my feed. So that's my logic. It's not your logic. Okay, I will leave the answer empty. I maybe test you in the exam. Okay, that's my habit. If you don't answer me, that will appear in the midterm. Okay, so let's look at the genetic bronze structure. Let's look at the top one. Look at the bottom right corner of these two. They look not that much different. You can argue to me the microstructures are different, but basically the shape look like a lot of curved worm, right? So, but the ray circles is the important information dimension. In such different dimension, one is like 100 nanometer, the other is 5 micron. And why this kind of structure look like repeat themselves, sort of, not identical, but I know, but sort of. This clearly means a consistent mechanism. A consistent mechanism control different structure, different dimension, but identical structure grown in different time, right? So a consistent mechanism grow consistent structures. Just about time. It's about the dimension, how large you grow, in what time. So that's a very two important technical detail of kinetics. You need to care the dimension. But the thinking clue is they look similar, sort of similar. And that means the kinetic mechanism most likely is identical in a mathematical way, in the same equation, all right? So you just calculate the equation in a longer time, the equation will spit out larger dimension. That's it. So you need to know the kinetic equation, of course, and how they grow the structure in what dimension at what time. So that's all kinetics. And the bottom one is just another simple example. You can see the line structure repeat itself, also in very different dimension. All right. So one is 10 micron, the other two are 15 micron, but the structure are aligned, right? So it's all about the original crystal structure and what equation you grow, and what equation of diffusion control the growing. If they are the same, it's simple the problem of shorter or longer time, and that's it. So focus on the common part with common logic. Compare the different part connected by common logic. That's why you need to think about and what the new capability you need to have in this class. Or you are wasting your time. You are not advancing your thinking capability. Okay, and I remember our professors are not working on MBE, but this is what my professor taught in the class. Yeah, because my department in the US have a lot of professors working on MBE. So my kinetic professor need to teach what kind of mechanism control MBE, the molecular beam epitaxy. And it's very important breakthrough for semiconductor field because it can grow not semiconductor only, sorry, and superconductor, semiconductor, and those kind of important materials can be grown in a very high quality, very good quality by MBE. So my professor taught us how to grow MBE, high quality film by MBE. And he listed the structural correlated picture on this page. You can look at the material on different acids, they grow different structure. It doesn't matter you have organic materials or inorganic materials. If the equation of diffusion is the same, and they will grow very similar structures. So it taught this in a single way, not separate into organic or inorganic. Basically, if you follow the common logic, and you will figure out that, this word is not like hard. Kinetic is not like hard. I just pay attention to certain important parameters, determining this crystal is what equation, the other crystal is what equation, this polymer is what equation. Basically, that's it. And it's not like challenging if you know how to think, if you know how to kinetics. However, if you guys never answer my question, never think, and most likely you will have really painful learning experience because this class is so different compared to your undergrad classes. Kinetics is a very different concept of class. It combines so many different classes. All right, so that's why it's hard. And you can look at it. So on this page, you have a crystal structure correlated diffusion, and that means you grow. If your diffusion equation is the same, that grow the same equation on the same crystal acids. If they are different, then it's different. So crystal structure, how they diffuse, driven by what effect, what's the thermodynamic driving force, and that's it. That's it. The kinetics is all about. So pay attention to the common part. And this is a very classic example in the semiconductor industry. Okay, you need to grow a high quality dielectric layer by atomic layer deposition. And hafnium oxide is a very strong dielectric. That can guarantee your nano transistor survives and the voltage like 5 volt, several volt, very small voltage. However, if you calculate it, if you bias the small voltage on nanometer, and your electrical field is large, right? And we have entered 2 nano era. So 2 nano era means if you have 1 volt or 2 volt, okay, 2 volt is simple. 2 volt, very small voltage, right? 2 volt applied on 2 nanometer. That means the electrical field is like 10 to the 7 volt per centimeter. Okay, that's very challenging because the electrical field is so large, like 10 to the 7. And basically, most of the material cannot survive. But hafnium oxide can survive. So that's why hafnium oxide is a very popular dielectric in the modern electronics industry. And because your transistor is so small, you need something really strong to survive on nanoscale. Sorry，喂，哎，我在上课，不好意思。哎，那个等一下我就要下课了，所以马上就可以了。好啊，一会见，拜拜。All right, so let's check if it's rest time. Yeah, take a rest and come back later. It's 10:10. I'm not so sure the alarm has happened or not, and I haven't heard that. So maybe we wait for 10:11 something. $86 people. Wow, more people. I don't know where you guys come from. There are so many. That's the first time in the past 3 years. Okay. Yeah, enjoy kinetics. Enjoy the pain of kinetics. This is really good. Uh, really good. I'm not saying I am good. I'm saying this class is good because my personal also learn a lot from kinetics. Okay, kinetics help my research a lot. Okay, I think it's about time we should start. All right, so Hafnium oxide. Okay, Hafnium oxide is a very important dielectric that can survive nanoscale and the voltage applied on nanoscale, a high electrical field. So, however, it's not perfect material because based on thermodynamics, you know, material always exists defect. Okay, there always exists defect in your material. Doesn't matter what that material is. You may argue to me, you are the good crystal grower. I grow single crystal. My crystal is perfect. And I can tell you, no, never perfect. Okay. Thermodynamics has told us that you cannot grow a perfect crystal. Maybe close, but never. Okay. So defect exists in material. And let's look at it. And now you look at the top layer on the hafnium oxide. You find it's aluminum nitride. So based on this is Professor Stammer's group. Okay, Stammer is an outstanding female professor in my department. Okay, and she grow really good semiconductor multi layers and this is the TEM picture she shared with Professor Levy, my genetic picture. So you guys can look at it on the top right corner. While you heat up the layer 700 degrees Celsius and compare that to 1000 degrees Celsius, and you can see some color changes, right? So some mesh, this kind of square or this kind of grid-like structure disappear, and some part like appear. And okay, so while you see periodic structure, that means you are growing crystal with particular structures, and the grid-like picture, the grid-like image means you are growing crystal structure. I don't know what that is, but certainly crystal. So like based on the image, PN image, you can see the color changing, the structure changing. I think it's changing, so it's kinetics. Okay, so some kind of diffusion happen in between those semiconductor phases or dielectric phases. And the bottom left corner was the original multi-layers of dielectrics. And on the right side, and you can see some small circle, arrow to other material. That means some atoms are moving. I don't know what that is, but clearly they are moving because color change in the TEM, right? So since they are changing structure, they are moving out of the material or they are entering the new material, you must have changed the structure and you know kinetic process happen. And we need to ask what that is, right? So compared to the left and right corner on the bottom, and you can see that's oxygen. Oxygen are entering into aluminum nitride layer, and that form a very complex composite with a different stoichiometry ratio between aluminum nitride and the aluminum oxide. Okay, so both oxygen and the nitrogen are really electronically negative atom. That's why they try to compete to grab aluminum. So aluminum is a very strong one, and hafnium oxide is less strong compared to aluminum oxide. So oxygen are taken. Oxygen molecules are taken from hafnium oxide, and that's the diffusion. Okay, oxygen leave hafnium oxide into aluminum oxide, and that's controlled by kinetics, driven by the electron potential difference. Okay, the driving force is thermodynamic, but the evolution process like the diffusion is kinetics. So you can also see hafnium oxide is stronger than silicon dioxide. So oxygen will diffuse into hafnium oxide, and oxygen will diffuse into aluminum nitride, and that's what diffusion happens. And after you leave the high temperature for a long time on the multi-layer, you can see new crystal appear on the interfaces. And that's the defect in your nano transistor. All right. That's why the nanoscale transistor fail, because highly conductive layer grows on the insulated interfaces. That's why your semiconductor will fail. And that's short, right? Because your insulator, the dielectric, cannot survive. It's no longer the insulating layer. It becomes very conductive silicide metal. Right? In this case, that's hafnium silicide. And that's very conductive material. Okay, it's alloy. It's a kind of alloy. So you need to know kinetics and you can understand what kind of defect happen, where, and in what scale, per time. So that's connected. You need to learn this. I guarantee you, I will test this kind of diffusion thing, defect-driven diffusion thing. Yeah, your oxygen has been taken by aluminum nitride. So your hafnium oxide is defective. And since it's defective, you have a certain part in metal, is hafnium. So that's very, very conductive. And that can form alloy with silicon, and that makes silicide, hafnium silicide. So your nano transistor fail like that. So if you are working in TSMC or UMC sort of semiconducting foundry, and then you need to know this. Or you are only working in a very simple electronic company, like you need to take care of wire binding, you need to take care of encapsulation. I forgot the English name for 日月光, okay? 日月光 is a very famous company that take care the transistor, the wafer from the chip from TSMC, okay, they cooperate. So they need to do this kind of wire binding thing. Like in the early 1970 or 1960, I forgot, in the early time of semiconductor industry, they have trouble for this kind of wire binding interfaces. And they found if they use different metals to do wire binding, for example, like gold and tin, and that's very common material on the motherboard, okay, on the circuit board. So the wire bonded interface just failed. It's controlled by diffusion too. So I designed problem set based on the true and critical problem in the industry. So I test people about this failed interfaces before. Sorry, that's not tin, that's aluminum. Okay, a tin will also have the same problem. Okay, I test this kind of two kind of alloy. All right, so people found the layer binding interfaces fail, and they know something changed. So they know they need to look for answer from kinetics because something changed. Kinetics teach you what kind of thing changed in what time. Okay, that's why kinetics is very realistic discipline. Discipline, sorry. Okay. And this kind of alloy will drive the diffusion happen because they have different concentration of atom. Concentration different will lead to energy different. Energy different will drive atom diffuse, and the diffuse atom will have kinetic rate to grow different structure. And people found that those alloy Al2Au and the other is ALAU2. Okay, these two are very troublesome and they have a bad mechanical property. So the bonded wire, the wire just broke. And this was a very serious problem in about 1950, 60. Okay, very early time. People know it now. So people had solved this problem. But that's also controlled by thermodynamic and kinetic. So you need to know that these two classes are very important and can help you. Okay. Oh, sorry, AL2, AU5. It's not, yeah, but AL, AU2 are very similar ratio. Okay, they are very similar ratio. So let's look purple. So people found the failed circuit look purple on the soldering area. So they found that the different alloy driven by kinetic. Well, you have this kind of interfaces appear on different atomic ratio, then you have trouble because their mechanical property are different on the interfaces. So just pump up, okay? They cannot no longer bond well because the mechanical are very different. That's why they break. Electron migration, I think I won't have time to teach that. As I remember, Professor Xu will teach that. Professor Xu Wendong, he will teach this. I think he has equation like that, but I forgot. And it's a very useful phenomena to explain the current induced effect. Okay, so basically this is all the topic I learned in the US. Okay, in a shorter time. You guys have 18 weeks, right? So we only have 8 weeks to learn it. I like 10, okay, maximum 10. 10 weeks to learn this, like almost half time. But the topic I can cover is this one in Taiwan. This one too, thermodynamic driving force and diffusion. I can cover that. But for other three, I can only choose important topic and important phenomena or important topic for you guys to learn. And that's why the classes in America is very, very challenging. Okay, they teach you so many things in such a short time, and I was really painful. That's why I told you, no pain, no gain. You need to learn new things in a hard way, or you never learn. You never challenge yourself. So I can cover the circle part, and but for the triangle part, I will choose some important topic for you guys to learn. If you want to challenge it, the same level like the US people, I try. Okay, I try. I try to cover many things in the first year, but student response was not good. That's why I only choose important and less topic right now. Okay, I would like to make sure you guys can learn the most important thing well, instead of squeeze a lot of things into your brain, but you cannot digest. It's not helpful. So I change. All right. Let's compare some important parameter in kinetic and thermodynamics. Okay, so the most important thing and the most important difference between thermodynamic and kinetics is thermodynamic define equilibrium state. Okay, equilibrium state means nothing will change. Nothing will change. Okay, about kinetic, you certainly moving something. So no matter it's steady state or non-steady state, you are changing your system by atomic fluxes. Since you heard fluxes, that means something moving. So kinetic and thermodynamic basically define two very different behavior. One is like nothing moves, call like equilibrium. And kinetic define something moves. Okay, we call that steady state or non-steady state. Either one are changing the system. So that's the key difference between thermodynamic and kinetics. And the driving force defined by thermodynamic basically means if you try to grow different structure, like different phases, like alpha, beta, gamma, whatever, you know they have different concentration or the ratio of atoms. So since I told you, concentration will change the crystal energy because different crystal structure will have different crystal potential. Different crystal potential will have a different binding energy. Different binding energy will give you different heat-free energy. Since you have a different heat-free energy, atoms try to diffuse because they want to go to lower energy area. All right, and while they try to move based on this energy difference, you give a driving force for them to move, defined by thermodynamics. But the moving phenomena, the moving thing, the moving property or the changing property is kinetics. Okay, that's the key difference. So it all depends on the judgment. All depend on if your material have atom moving or not, and if they move, in what speed, and that's how kinetic can tell you. So, summarizing, its structure or property changing various time, and that's kinetics. Okay, so that's the key difference between thermodynamics and kinetics. All right. So since you have learned that thermodynamics can tell you the energy difference, so basically, if you are sure you have energy difference between systems, you know you have an initial state before they diffuse. You know you have a final destination for their moving as a moving target, right? So you need to use the energy difference defined by thermodynamics to come out the driving force. Then your material will diffuse. Then the diffusion is the most important part for you to learn in this class, the kinetics. So something moving, we analyze something moving and what speed. All right. So kinetics give you the information about path, and the thermodynamics basically define the source material and the target material. So that's the map. Thermodynamics can teach you how to move, and I should say where to move. Okay, sorry, not what to move. Okay, where to move. That's the map, right? You look at the map, you read the map, you know the target. But how you reach the target, the path can be very different, and that's kinetics. Because we can use a different kinetic process to determine how your atom should move from the same source to the same target. You may have a different way to move it, right? For example, if I use the whiteboard to draw something, okay, let's pretend this is a phase diagram. And I don't care what that is. So A atom and B atom. Let's use a very classic eutectic as an example. Okay. If you choose target, color may be less clear. Maybe use darker color. For example, if you have melted the metal or the semiconductor, it doesn't matter, then that means they are in liquid state, right? You know your material on, and let's choose the ratio. Okay, here I just take a random ratio. Okay, so you are sure you have to heat it up to this temperature. So thermodynamic phase diagram tells you on this rate, based on this ratio, based on this temperature, your material is liquid. And now you would like to grow certain solid solution, a certain solid in certain ratio. For example, your target is here. So you know you need to lower the temperature, right? You start your phases here. You precipitate out from these phases, or in the process they are doing phase separation. Because you lower the temperature, you reach this part. So you need to have these two phases, right? However, if I say I use very short time, controlled by diffusion and kinetics, to grow different ratio, how? You say you are going in this way, so you can only come here. I say no, I can use that. I can change the path by kinetics. So I choose a certain point while the diffusion is happening from this ratio changing to this ratio. I choose particular ratio in particular time. So I can also grow this ratio. Then I keep lowering the temperature. And I come to different paths. That's why kinetic can choose different paths. And then you say you have deviated from the original target. Yeah, you are right. So how can I go back? Can I go back? Yeah, of course I can go back. Okay, because I know when I reach this temperature and you will have space separation again. Try to go to these two targets, right? So I can come back here. Control by what? By diffusion. Okay. So that's how you change the pathway, how you change it by different kinetic process, different temperature, different concentration, and that's kinetic. But you have the thermodynamic map, phase diagram. So you know your start, you know your end, but the path depends on you. Okay. So you can use a different kinetic mechanism to limit the precipitation or limit the diffusion, changing the concentration, and then you may or may not reach the final target in different ratio, right? So that's how you combine thermodynamic and kinetics and lead to your target. Okay, go back to slices. Okay. And that's basically the top half behavior. And now you look at my mouse. You know diffusion takes time. And what does this mean? The rate depends on energy of activation energy. This delta U ACT mean activation energy. What does that mean? Why energy is correlated to the rate, to the kinetic process? This guy just told us that the energy is defined by thermodynamics. Why suddenly this rate, clearly a kinetic parameter, is also determined by energy? This guy is bullshitting me, okay? Oh my God, no, I am very honest, man. So that's a different concept of energy. And if we are sure we have a diffusion mechanism, 100% kinetic phenomena driven by thermodynamics, right? So let's look at the next page. If we are out of the 0 degree or we are out of equilibrium, we are reaching either steady state diffusion or not steady state diffusion, something must move. That's why I mentioned that energy is correlated to kinetic. And this page is the answer. And remember this page. So sorry. 不好意思，我在上课。对，来，等一下下课之后你可以打来，没关系。好，OK，拜拜。I'm so sorry, my colleague phone all the time. Okay, so remember this page. These pages are very important because it has been the whole story of kinetics on this page. So I labeled the blue symbol as a thermodynamic parameter, and I labeled rate force as a kinetic parameter. So now you look at, and I say mobility is defined by kinetic, yes, a very important part. Okay, but how about the flux? And now you see the energy diagram on the bottom left corner. And this picture has finished the kinetic story already. Okay, the whole kinetic class is here. Okay, on this bottom right corner. So that's because the energy, you look at the energies of the alpha phase and the beta phase. I told you phases are defined by the thermal equilibrium, so it's defined by kinetic. So the number one, the alpha phase, try to go to the lower energy. Number three, beta phase, right? Because beta phase has lower energy based on this diagram, energy diagram. So the driving force is defined by the energy difference between alpha and beta, between 1 and 3. So that energy difference gives you delta U alpha to beta. And that's the driving force defined by thermodynamics. However, you look at the barrier here, look at my mouse. Before your atom can move from alpha to beta, you need to overcome a barrier. That's a delta U activation. Okay, that energy difference defines how quickly or how slow your atom can proceed the flux driven by delta U alpha to beta. So your atom must first overcome this delta U activation, then they can flow to create fluxes defined by delta U alpha to beta. And this picture has explained the key difference between thermodynamics and kinetics. So the thermodynamic state must be defined by equilibrium, right? That means nothing moves. I told you, nothing moves means nothing change. So the energy must be zero. Then you look at the alpha and the beta. The energy, the red line here, is flat, right? It's a straight line with a particular value. That means alpha and beta cannot change in themselves. But alpha try to move atom from alpha to beta. So slow the diffusion happen, defined by the energy difference here and here. Energy difference between alpha and beta, between 3 and 1. But for only 3 and 1, they are equilibrium state inside the state, or for example, like crystal 1 and crystal 2, and crystal 3, or crystal alpha or crystal beta. Nothing moving, right? Nothing moving because the energy are the same, because the concentrations are the same everywhere on different area. However, on the interface between 1 and 3, between alpha and beta, atoms are moving. So diffusion happens. Most likely driven on the interfaces, then it propagates. It changes the whole system. The whole alpha will change into beta in a very long time. All right. How quickly or how slow, I don't know. Maybe quick, maybe slow. It's not my decision. It's a crystal decision. Then you know the blue part can explain the thermodynamic property, like 1 want to go 3. But the 2, the kinetic delta U activation, define how quickly they can go from 1 to 3. And now the kinetic has finished it. Yes, we don't come to class for the following semester. Yeah, you bet. Okay, the key concept has been done here. All right, remember this page. That's the kinetic all about. Okay. So the transport resistance means how quickly you can overcome the activation barrier. Okay, the activation energy delta U ACD. And so that's a concept like how quickly you can move. So we can also use a type of resistance to think about it. If the energy is large, the barrier is high, then the process is really slow. So atoms try to resist the diffusion from 1 to 3. So because that step 2 is really challenging to overcome. So atoms don't want to do that. They just try to stay in alpha, and atom B will try to stay in beta. All right. So the key difference has been done here. Okay. So I think we are almost done for the introduction, but tiny bit concept left. So let's think about the diffusion in solid. So the bottom right corner just a repeating picture. Just like the previous page. So let us think about the state function. State function, you have heard this in your undergrad thermodynamics. So that means it's defined by the thermodynamics. That means it defines the energy of the state. Inside the state, nothing can move. But now you have to learn that on the interfaces, diffusion happens, something moving. And then this moving will change the structure forever. But in what time scale? That's the question you need to ask in kinetics. Okay, kinetics will teach you how to calculate that. Is that fast or slow? Kinetics will teach you. So that means most likely you need to focus on, and look at my mouse, focus on this energy barrier for kinetics. However, I will test you the whole flux calculation. You need to know the whole picture totally. Because I will ask you to calculate fluxes. And the fluxes is a combination of your delta U activation and delta U alpha to beta. So you need to know both, right? And that's the combined concept of kinetics and thermodynamics. That means you need to consider the driving force. Driving force. The driving force in the center of the slide and the mobility in the system, how they diffuse in what speed. And if you increase the Gibbs-free energy difference by changing entropy or by changing enthalpy, okay, you can use delta S or delta H to change the Gibbs-free energy delta G, right? You have known that. You learned that in your undergrad. So entropy can drive the crystal diffusion, and entropy and enthalpy can also drive the crystal change, crystal phases change, because the energy are purely different. So that's thermodynamic driving force. And system try to minimize the energy. That's why atom try to diffuse to lower the total heat free energy in the system. And that's the kinetic all about. They want to happen or not, it's defined by thermodynamics. How they happen in what speed and like how fast they can move, it's defined by kinetic. And we call that kind of thing like diffusivity or mobility of atoms. Okay. All right, and after system optimize the system structure by minimize the free energy, they reach another new equilibrium. So again, nothing moves. All right, and that's the whole kinetic process all about. And that's has been summarized in this picture. That's why this picture is very important. You need to know this all the time. Okay, try to use this picture to analyze your research topic. And because you guys come from different research field, but kinetics are everywhere. Kinetic phenomena are everywhere. While you are changing the system, you need to know kinetic process, right? So remember this bottom right corner and try to apply it to your research topic. Okay, I would like to drink sip water. Wait me several seconds. All right, so and now you look at the comparison to your fundamental physics. And you take a ball high, you drop it, the ball will drop, or you put it on the top of a slope, okay, a steep slope or something, and then the ball will rolling down the hill. So that's energy difference driven by the gravity potential. And it's the same like the crystal changing their structure, because one phase has a higher energy and the other phase has lower energy. So this kind of ball just flow. You can imagine the ball is the atom in your system with a higher energy. Of course, they try to move to lower energy, right? It's a natural process. It won't happen because the energy is lower in the new equilibrium state. And this simple gravity potential can also explain the kinetic fluxes in crystal. So physics is very universally correct. You need to have good physics or you will have really painful kinetic class. And driving forces is defined by the energy difference. Here on this page, that's gravity potential and GH, right? But in the crystal, that's a heat free energy and of your crystal from alpha to beta. So, and try to remind yourself of this bottom right corner all the time. Okay, that's very important picture that cover all theory, the most important theory of kinetics. Okay, you can use this picture to help you thinking. Atoms need to move from higher energy to lower energy. An easy way to understand it. Then let's take diamond as example. Diamond is a very classic example that teach you kinetics. Okay, based on this page, the bottom left corner, diamond is in state 1, and graphite is in state 3. Clearly, diamond has higher energy than graphite. But you can check the wedding ring you give to your wife or you give to your husband. Have you seen your diamond ring degrade into graphite? And your transparent and shining diamond ring turn into black graphite? Or if that happens, your wife will divorce with you. Okay, How dare you giving me fake diamond? No. Okay, you need to teach her or him. You put your diamond in the wrong space. So the activation barrier, you can see originally the activation barrier, delta UACT, from diamond to graphite, original barrier is really high. But maybe you put it in a strong AC or high temperature, how could I know? Okay, I don't know what you have in your house. If you put it into a very extreme environment and that lower the barrier or that increase the the background energy, look at the mouse, it raise the energy high in this kind of extreme environment, diamond will turn into graphite much easier because you decrease the barrier high, right? So diamond and graphite is a very classic example to explain the genetic barrier concept. Because the barrier for diamond changing into graphite is really, really large. So the rate is really, really low. Because I told you the mobility, if you look at this equation, mobility is proportional to the reciprocal of energy. If energy is high, that means the determinant is large, so the mobility must be low. So it's almost like impossible to happen. And that's the key concept. So since the barrier is really, really high, so your diamond won't become graphite. Okay? Make you feel comfortable. Diamond won't turn into graphite, or maybe later, like 1 million years. That may happen, but not this, not in your life. Okay? So if diamond are forever, or love are forever, it's questionable. Okay, depend on the environment. Okay, if you to live in a harsh family with less financial situation, you are in trouble. You may divorce. So love and diamonds are both not forever. However, if you put them in a stable environment, you are stable. So your love is forever. All right. So the genetic barrier is high. If your genetic barrier is high, from waiting to divorce is really high. For example, you have a kid, you have good money, income, and the environment is stable. So diamond won't turn into graphite. You are safe. Okay. But this is a very classic example. If you give a very extreme condition for diamond with a high temperature, high energy, diamond will turn into graphite. All right. So you may divorce. Okay, the love is not forever, but it may be 1 million. Okay, 1 million years. So you are safe in your lifetime. Okay, that's a classic example to explain genetic barriers. All right, that's a summary. And after this summary, we may take a rest and come back 10 minutes later, but not now. Let's look at what we have learned. So first, if your system is changing, that means you are moving atoms from high energy to lower energy. And you know that happened, so you have thermodynamic driving force. Then the genetic will tell you how quickly or how slowly this process happened. So the path in what rate. Okay. Actually, I should label the path as rate. I'm so sorry. That's genetic because you can choose different paths to reach the same thermodynamic targets. So I should use path in rate. Sorry, I will fix that. And for your kinetic process to happen, first you need to have a driving force. And the driving force is defined by thermodynamics, so I use blue. For example, like different energy, okay? And then that will drive the atom moving in your system. Then we can use that energy of the barrier, delta U ACT, to calculate the probability for this kind of diffusion to happen. And that's the probability for your atom to move from 1 to 2. You need to go through number 2, the barrier. So that barrier determines how quickly and how slowly the diffusion fluxes can be. and that depends on probability. So it's all about energy dependent probability, and you have learned that in thermodynamics while you were undergrad. So remember what you have learned. All right, then the rate determination, I will teach you that. Basically, there are two kinds of physical process. One is series, i.e. number 2 need to wait for number 1. Number 3 need to wait for number 2. So number 4 need to wait for number 3. While you need to reach from 1 to 4. And then you need to go through 1, 2, 3, 4. We call that series processes. And the typical example is melting process and the solidification process. You need to wait for all the mechanism happen, then that will happen. And the other example is parallel processes. Parallel process. And a classic example of that is catalyst process. So catalyst always go for the fastest way because that happens in the same time. If you provide the system two-way, that for example, like the original surface covered by gold nanoparticle, okay? Gold nanoparticle is very famous, or platinum nanoparticle on some kind of composite, like Indian nitride, something. I don't care, but the catalyst happen. If you provide different tests in this way, let me draw a simple picture to teach you what's the parallel process. For example, process catalytic. For example, you have a nanoparticle. I don't know what that is, maybe an Indian nitride or whatever thing. And people use that to generate hydrogen. And you would like to make water split happen faster. Or you would like to downgrade or decompose a certain contamination molecule. Typically, people put heteromaterial, a different material on top of it. Okay? I don't know what that is, maybe platinum, I don't know. It depends on the system you are working on. I just take this as example. Okay. If your water molecule like blue, if your H2O can reach both interfaces, so you provide process 1 and test 1 and the test 2 in the same time, right? We call that parallel process because theoretically your water can reach both interfaces in the same time. However, which one determines? Okay, which one determines the rate? And this is the class spirit of parallel process of kinetics. And the fact is one dominant. Okay, the fact is one dominant. If you compare this to the series process, that you need to melt into alpha, go to beta, go to gamma, go to liquid. If you were melting, it's determined by this kind of a series process, and we call that series process, right? Then what process to dominate? Alpha to beta, or beta to gamma, or gamma to liquid? The slowest one dominate. The slowest one dominate in the series process. Okay, it's all about genetics. Because you go through alpha, beta, gamma, then liquid. So the slowest one will determine the rate of your genetic process. But for this parallel process, this is the parallel. The fact is one dominant. For example, this interface is very active. So all the water will come here because this one is much more efficient. And this one is The fact is one dominant. Will determine the speed of your kinetic process. All right, I think it's about the rest time. Yeah, it's 11. Okay, I control the time well. That's it. And I think we have done the introduction. Let's take a rest. The next class will be the kinetics. Okay. Right. Okay. So I think we are done. Take a rest. Okay.哎，张老师，我是方玉。哎，什么事？没问题，怎么样？永远都没有把我还在改变我的，要赶快投啊，不然我就被 fire 掉了，大哥。我想当你的同事啊。哎，那个，如果你给我多一点时间，我可以帮忙啦。哎，上一次那个真的太赶了。哎，好啊，那你给我吧。哎，OK，嗯，对啊，OK 啊，对对，太赶，你就不要逼我了。对对，哎，感谢你啊，谢谢，拜拜。哎，怎么样？好好，没问题，OK，拜拜。 Jane. Oh, yes. Yeah. Thank you. Hello. Hello. It is 11:10. Again, I didn't hear the alarm, so not so sure. But I think we just start. All right, guys, we just finished the introduction about the key difference between kinetics and thermodynamics. You have learned the important difference. Take care to the energy barrier. I remind you that's the most important theory of kinetics. The energy barrier that can drive diffusion happen. All right. So pay attention to the energy diagram and then try to apply it to your own research topic, and that can make you have clear picture about kinetic and how that happens in what rate. And all right, let's start the real kinetic parts. Okay, then I will just share the monitor. Okay, so why we need to learn defect? Okay, now you look at the topic. Since I mentioned defect and diffusion, that means the kinetic process of diffusion must be highly correlated to the defect inside the crystal, right? If we take inorganic composite or inorganic metal, whatever things in the same time, we need to know why we need to learn defect. And there are so many different kinds of defect. You can simply consider defect as a broken crystal or broken binding fiber. So originally, you know they are bonded, right? Those atoms are bonded. Since they are bonded, they share energy. They were stable originally. So they were in a thermal equilibrium defined state. And the logic tells you if they were defined by thermodynamic equilibrium, that means their energy is low. But now you break it. Okay? Now you break the binding. What happened? What happened? So you need to frequently ask yourself, and then you need to frequently try to answer my question, either in public, speaking out, or you think about it in your mind. You ask yourself this question and think about it. Since they were defined by thermodynamic equilibrium, so they were in a lower energy state. Now you break it, so they are in a higher energy state. That's why defect can drive diffusion happen. Because you destroy the thermal equilibrium state of a crystal. So the defect side now has a very high energy compared to the initial state without any broken bonds, right? So that's why defect will drive a kinetic diffusion happen. Now you need to know this logic, all right? It's not something you memorize. The logic tell you so. It's not because I tell you so. It's because physics tell you so. Trust physics. Trust thermodynamics. Trust fundamental physics, chemistry, whatever. Then you will have an easier learning experience in kinetics. Now, since we know defect has high energy, and you now need to learn different kinds of defect in different kinds of crystal. So like we are determining the kinetic diffusion in different rate. Okay, so crystal matrix, because crystal structure with different composition, whatever matter. That's why the defects are all different in different crystal acids or different composite ratio, right? So, and in the first year, I could cover this location, but since we have online lecture, I'm not so sure. But I will try. Okay, so 2D defect also can drive crystal growing behavior. Certain crystal will try to diffuse atom into the other kind of crystal domains through the boundary. So that's a 2D defect. In the first year, I also could cover that, but I'm not so sure now. And for 3D, that's too large. It's out of the kinetic class you feel interested, because most likely we try to grow good quality of materials, right? And then that kind of material has lower concentration of defect. So typically you need to take care of defect in much smaller scale. For 3D is too large, so we don't teach that in this class. And of course, the whole diffusion is driven by the fluxes. And on the bottom corner, if you want to calculate the flux of the kinetic diffusion behavior, then you need to take care of the driving force as well. So you are not only required to learn kinetics, you are also asked to calculate thermodynamic variables. You need to learn both because the combination of thermodynamic and the kinetics are the whole picture that can define the diffusion. Okay, so the first target, effect. The second target, the diffusion rate. Then you have learned probably more than 60% to 70% about kinetics. Okay, we just take different example again and again in different equation. Or equation is the same but different parameter. That's it. All right. So you know the important target is effect and the diffusion. And typically we think about the zero dimension defect. That's the point, right? So either you miss an atom or you have an extra atom, and we call that zero dimension defect. And this picture defines the vacancy as a zero dimension missed atom site. Okay, and look at the interstitial, like you see an extra atom squeeze into the site that was originally not allowed for it to get in. And we call this kind of defect interstitial. That means something you insert as an extra. All right. So, and you may see we also can insert a very small impurity into the host crystal. And we call that impurity, or you can call that solute, because this is a combination of two different atoms in one solid, right? So that's an example of solid solution. And the right one is very classic dislocation. And if it's polymer material, then that's discrimination. I will try to cover that, but I cannot guarantee. At least you will learn the most important behavior, kinetic diffusion behavior defined, driven by zero dimension defect, and that's the most important one for most of the material. It doesn't matter semiconductor or ceramic or metallic. Okay, it doesn't matter. And if you have zero dimension defect, that's the source of the driving source of the kinetic diffusion. And boundary or surface are also very important, where you have two different crystals try to meet each other. And then we'll have different diffusion rate through the interface. So typically, large grain will hit the small grain, and that's thermodynamic driven phenomenon. And I try to cover that because it's interesting, and I will try to cover that too. So basically, you will learn the structural evolution, zero dimension, one dimension, two dimension. I will skip three dimension. Too large. That's not very modern for the most modern kinetic concept. All right. Okay, the very classic example. So now you look at the equation first, then we go to the whiteboard later. The most important thing is vacancy of missing atoms, all right? But why you see the Boltzmann distribution, you should ask yourself, not only memorizing the equation. So when you think about what I have mentioned, you know it's all about energy difference, right? So Boltzmann distribution basically defines the deviated state and the equilibrium state, the happening probability for this deviation to happen. That's very simple description for Boltzmann distribution. Based on classical physics, but you will find out this surprisingly matching whatever quantum system. Because even now we still use very simplified model to model based on Boltzmann distribution to describe whatever quantum thing. If we try to solve it in a simple way, so Boltzmann distribution tell you if you have the energy required for the forming effect and for this event to happen, it's that energy divided by kT, and don't forget the minus sign inside the exponential coefficient, right? Some of you may learn this, some of you may not. I don't know, because you all come from different departments. So I will try to cover the simple derivation. So let's look at a very simple model of the derivation. Probably most of you have learned this in undergrad, okay, based on thermodynamics. So let's come to the whiteboard. By the way, if the color is too light, tell me anytime. So now we need to know the concept of thermodynamic distribution. Boltzmann is defined by the very classic physics and defined by thermodynamics. And it's all about energy, right? So you know thermodynamics gives you free energy equal to your crystal potential, the mechanical work divided by the system entropy. And you know this is not happening, at least in this case, okay? Sometimes it happens because some of you may need to strain your semiconductor, like you strain silicon by different crystal structure below. So some of you may need this mechanical part, but most of you don't. This one, yes? Anyone say? No? And so now you know if we ignore the mechanical part, and this crystal potential basically is the binding energy of enthalpy. All right, so the physics just flow like that. That's logic. And if you would like to change your physical system, you need to consider gift free energy, like how well your system can change. And that's determined by this. Okay. If we consider a perfect crystal, that's atom. We have a total capital N atom. Well, we have a certain portion of the gray square as empty part, nothing here, to address the concept of vacancy. And we call this number like small n. I don't know how many, but that's it. And based on classic physics, you have learned over the senior high school math. You know it's all about the combination. How you can put atom into so many sites with a certain portion of empty. In what portion? The portion of small n divided by capital N, right? So how many combinations we have? Thermodynamics tells you the combination number of this kind of mixing system will give you equilibrium energy. Okay, so that's the spirit of Boltzmann distribution. You have so many ways to form your crystal. Well, I just put those things in different crystal sites. So how many? How many? The number. If I say it's like I use a combination number like omega, and you know the combination is the total size divided by the site that's occupied by atom and occupied by vacancy, the number of this one, right? So that's total number. The biggest contribution from Boltzmann is this smart genius figure out that, oh, I introduced a way correlated to numbers, a certain number way to form my system, the same system, but in different combination. And the energy can be explained by the concept called entropy. And Boltzmann say entropy is equivalent to the Boltzmann constant natural log of this omega, the combination weight. That's how many ways you can form this system or form this crystal. And then we put this one into here. And now we have the free energy. That's how you define the whole system based on thermodynamics. Someone asked me to share. Oh, yes. I'm so sorry. Yeah. Thank you for reminding. Okay. If the system has a total heat-free energy, that means what's the energy state it is. Then consider the binding from the original definition of mechanical work plus your potential. You don't consider this as a typical crystal. When you don't strain your crystal, then you have binding and subtract subtracted by P entropy. And ultimate contribution is based on, you figure out that the way of how many combination of the system, and we call different way or different micro state. How many number of micro state will determine another energy term called entropy. And the number, take the natural log of the combination number, multiplied by the Boltzmann constant, that gives you energy term based on joule per temperature. And we know that's Kelvin. See, I say Kelvin, that's the temperature. That's the entropy term. And you multiply that by temperature, then you form the same unit of joule, right? So entropy multiplied by temperature gives you energy. And so combination number become energy. And that's the thermodynamics, one of the most important concepts. So after that, we put this in, and after we figure out this, we put that into heat-free energy. And we know the binding doesn't change. So we don't need to take care of that for now. And the equation, the energy to form vacancy, count the binding energy of your enthalpy as a constant, subtracted by P, natural log is for omega. And we put this combination in. And that will give you the total heat-free energy of the system, the capability to do work, so the capability to change the crystal. All right, so because we only take one vacancy as example, we just take one spot as a target to analyze. And this one can be considered, the total enthalpy can be considered to how many vacancy I have, multiplied by the energy to destroy it, i.e. how many binding energy how much binding energy I need to destroy this crystal. Then I connect this enthalpy to number and take the natural log. In K, I forgot the Boltzmann constant, sorry. And this factorial can be simplified by Stirling approximation. You can Google that and you know how to simplify it. Stirling approximation. So we need more space. Berlin approximation like color look like. Okay, search this. This one tell you factorial equal to this one. Okay, use this one, put it into this equation, then you will find the answers. Oh, done here, sorry. This is the first one. Second one. Take the derivative of both number. Okay, this is the variable, right? You know, if I want to reach an equilibrium state, my energy must be minimized. This must be zero. After you take the derivative of first order of derivative, then you know the minimum energy for heat free energy, like G vacancy. Now you try your crystal try to form vacancy defect, and use this tool and put it into the original equation here. Then okay, calculate that by yourself, and you will have divided by kp equal to the natural log. Capital N subtracted by small n divided by small n. Then answer will be your n divided by, because the number of vacancies is much smaller than n, so I will approximate it as this one. Okay, this is how you derive the probability to form a vacancy in a crystal. This is the vacancy number. This is the crystal atom size. Okay, so this forming probability is defined by Boltzmann distribution. Not hard, right? I expect most of you has learned this in your undergrad. And figure this out by yourself. You can use this one, put it into the original equation to finish the calculation. Then finally you will reach this step. So what this equation can teach us, that's more important. So let's look at the slides. Share it. Okay, let's look at this page. So while we try to form defect like vacancy in particular crystal, we don't know. That's one kind of crystal. So let's assume the formation energy is that 1 eV. You look at the bottom left corner. So the probability for this defect to appear is calculated by Boltzmann distribution that we just finished. So you put 1 eV as -1 divided by what temperature I define? Okay, 1000 K at 1000 Kelvin. After you calculate it by your calculator or whatever, so the probability is about 10 to the -5. So you have one vacancy appear per 100,000 atoms. So it's not high. So it's not, or we can just say it's about 10 vacancy per million atoms. So very small portion, right? So that's how easy or how hard you can have the defect in a crystal, and that's defined by Boltzmann distribution. So play with those equations, you will have more feeling about it. I suggest you do that, and you can put different number, or you can Google different atom defect energy. then you can put it in and quickly calculate the probability forming crystal. Or you can choose your own research topic to calculate it. Yeah, just Google it. So you can find most of the answer and find most of the parameters you need. And that's why I told you guys, you should not just copy the whole answer and then write it in the note, because I changed the system. And you copy that number, you will be in trouble. All right, I will just first you lose the original point. Second, you lose the bonus point because you violate my rule. Okay, let's think what's next. All right, there's another kind of point defect. Let me remind yourself. Go interstitial. Okay, let's look at this page. Zero dimension defect like vacancy is very clear that we just finished the derivation. The energy is proportional to Boltzmann. Let me ask you one thing. If I take the same atom and squeeze it into the side that was originally not allowed, and I just take one identical atom and squeeze it into the interstitial side, what kind of energy I need? Okay, what kind of energy I need? Because now you have learned the probability of defect in your crystal is highly correlated to your formation energy of that defect. So vacancy has vacancy's energy, interstitial has interstitial's energy. How if we take atom, i.e. we take away to form a vacancy and then squeeze it into the same crystal, what energy we should expect and what probability we should expect? And now we give you this example, the equation. Okay, let's quickly look at the physics. Let me leave the share. Okay. Now let's look at it. You know the probability forming vacancy. How if I take an I atoms and then put it into interstitial side, I side. And this is the probability forming interstitial defect, right? Because I take original atom in and put it into the interstitial side in the same crystal. So I form vacancy first, and then I squeeze the atom into the interstitial side. So it's correlated to two energy. One, vacancy. Second, interstitial, because I need to squeeze the atom into the interstitial side. So that takes extra energy. So it's correlated to two kinds of energy. First, your vacancy must be formed first, because you need to take atom out. Second, you need to squeeze that atom into interstitial side. You need to distort the crystal. Then let's look at the probability forming interstitial defect. And this is called self-interstitial. That means you take the same atom, put it into the interstitial side. We call that interstitial, self-interstitial defect. Okay, so based on the process we have learned, you know it must be highly correlated to its potential, the Boltzmann distribution. But how? So now we need to think about two kinds of process. Imagine that you have a crystal site. If I take the atom originally on the cross spot, okay? Broken binding. Take this atom out, so it's empty. It's empty, just like the original empty vacancy site here. Then make the empty, so you form the vacancy of ink. Form the vacancy, and you squeeze it through this side. So you form the cell interstitial. So you need two kinds of energy to satisfy this physical process, and that's a series process. Now you know why I need to introduce your series process and the parallel process. Clear series process, right? First, you need to take one atom to form vacancy. Second, you need to squeeze it in. You need both in a series. That means you need to multiply two events probability together, and we call that series process. Okay. So let's look at it. The number of vacancies. Clear what you have to learn. Look at the combination number of interstitial. And remember, we defined it by capital I. And you may ask, hey, why you change your capital N into capital Ni? And this is the I side in the crystal. That means that's all this space. Okay, this one, that's now I, I, all the I side in the crystal, right? Of course, you change your capital N to Ni because you have a different interstitial side compared to crystal side, right? This cross spot as crystal side, but now we are thinking interstitial side. So we need to use the interstitial side number to calculate that. So this is the combination of your total probability and total combination number. Then both of them need to happen. They need to happen in series process. So you know the meaning of a series process. That means two events must happen in the same time. So the probability must be the combination, or the number of the combination must be the multiplication for both of phenomena. So the equation change. The total combination number equal to these two. Multiply them together. Then you put it into your entropy equation. Right? We say prop because it's different right now. Okay. So this is the new combination number for entropy. Then you repeat the process again. The same way to calculate it, the same way to finish the derivation, use Stirling approximation, and you take the first order the derivative to be 0. So this one to 0, reach the answer.